We're going to start with 831. Hope this video finds you doing well. This is going to be something we've already talked about a little bit this year, so hopefully this will not seem super difficult or surprising. Just the idea of the way dimensions work and how things grow as the dimensions change. So if you have length, obviously that's in one dimension. It just goes left and right. I mean, I guess it could go up and down if we were looking at height. The idea that we're just looking at one dimension, not at two. So if we start with something with a length of 3, its length is 3 in one dimension. If we have something with a length of 5, its length of 5 in one dimension. When we go to area, though, we're looking at a second dimension. So if we turn this into a square with 2 dimensions, now all of a sudden we see that we have an area of 9 units squared. I guess I should go over here and say like 3 units and 5 units, right? Units to the first. We don't need to put the 1, but if we want to, if it makes us feel better. So you can see the way this grew is it actually became 3 to the second power, right? So that's going to be 3 to the second power. So likewise, this is going to be 2, 3, 4, 5, 2, 3, 4, 5. Same thing. We're going to get 5 to the second power, which is going to be 25 units squared. Again, simply by going to area from length. Now, if we go to volume, and this is going to look not good, so I apologize, it will turn into a cube. So now we have width, height, and depth to it, right? So, and again, this is not going to look great, and I apologize for that, but hopefully you can sort of visualize the idea that I have all, that looks really bad right there. Well, none of it particularly looks good, but even worse than I wanted to. Okay, so now if I have these little cubes that I've cut this into, it's actually going to be 3 to the third power, or 3,927 units cubed. Same thing here, and I won't even bother trying on this one. It's going to be 5 times 5 times 5, so it's going to be 5 to the third power, or 125 units cubed. And what I want you to see is how quickly it grows. Here it only started out 2 different, but because we squared it, now it's 16 different, and because we cubed it, now it's 98 different. So you can see things grow rather quickly when you change the dimensions. The bigger the number, the more quickly it grows. The smaller the number, the slower it grows, but you can see it still grows rather quickly. So that's the concept we're going to look at. We're actually not going to talk about volume today. We're going to simply focus on length and area and the relationship with that square. But I wanted to kind of talk about volume just to set the table for what's going to come later. And at that, we will begin the lesson out of the book. This might take a while. I'm sure there's a better way to do this. I'm still trying to figure out exactly how the software works the best when I use this. So I knew eventually that was going to appear, and then anyway, all right. So let's go ahead and begin. So it says, Mighty Mascot. To celebrate the victory of your school's championship girls ice hockey team, the student body decides to hang a giant flag with their school's mascot on the gym wall. To help design the flag, your friend Archie creates a scale version of the flag measuring 1 foot by 1.5. So there we go. It's 1 foot by 1.5 feet. The student body thinks the final flag should be 3 feet tall. So they want it to be 3 feet tall. So you can see we doubled it in this dimension. The question is, what's going to happen if we double it in this dimension? How wide would it be? Well, in theory, it should double as well, right? That's what should happen. If Archie uses $2 worth of material to make the scale, how much is this one going to cost? And I think this is where we sort of run into some confusion a little bit at times with people. So what if we go over here, and I'm trying to think. I thought I had a page opened up for that. So let me go to 831. And let me open to the resource page. And so you can see it's more of a scale. And really what I want you guys to see is that this scale, if I go 1 foot here and 2 feet here, I wish I could write on this and I can't. You can see though it's split right down the middle in this direction. And then if it was 1.5 foot here and it was 3 feet there, I'm actually splitting this big thing into quarters. So I'm going to go back over to this software and sort of draw what I'm trying to describe here. So if I look here, I hope we agree this would be 1 foot and this would be 1 foot. And I hope we agree halfway down this would be 1.5 feet and this would be 1.5 feet. Well, if I go that whole way through, how many of the little pennants am I actually getting in the same area as the big pennants? I'm actually getting 4 times, and that should make a lot of sense because I'm making it 2 times bigger width and I'm making it 2 times bigger height. So altogether, I'm making it 4 times bigger, if that makes sense. So if I'm spending $2 here, well, I would expect to spend $8 here. Again, I hope that makes sense that we have those 4 little pennants. It's not twice as big. It's actually 4 times as much area. All right, so moving along. I don't know what all this is. Clear all this out. For some reason, that's in the way there. It's weird. I don't know what I did there to mess that up. Okay, carefully cut enough copies. Obviously, we did that. The student body is reconsidering the size of the flag. It is now considering enlarging the flag so that it is 3 or 4 times the width of Archie's model. How would the materials for this similar flag if it's 3 times B? Well, again, you're looking at a much bigger flag. Here it's 1 by 1.5. If I make it 3 times bigger, it's going to be 3 by 4.5. And if you think about it, now when I break this up, I'm making it 3 times wider, I'm making it 3 times taller, so I'm actually making it 9 times bigger. So that one, if I did the 3 times, I'm gonna actually have to spend $18, and that's the 3 times bigger. If I made it 4 times bigger, and I guess I'll put the 4 times bigger down here. If I make it 4 times bigger again, now 2, 3, 4. 2, 3, 4, you can see I'm actually making it 16 times bigger. So if I have $2 and I'm going to make it 16 times more area, that's going to be $32. Now think about how quickly that grows. Again, you're saying, but I'm only making it 4 times bigger, yet you're having to spend 16 times more money and use 16 times more material. Again, because it's not growing 4 times bigger in this direction only, it's also growing 4 times bigger in this direction for a grand total of 16. So again, they have a tendency to get away from you really quickly, especially like volume. When we get later in the year, we'll talk about volume, and you know, when you make something twice as big volume wise, you're actually making it 8 times bigger volume wise, because it's 2 times 2 times 2, so it really does grow quickly. But again, we'll save that for later. So write down any observations you found while working through the problem. Again, hopefully we're okay with the idea that it's actually, you know, if we make it 2 times bigger, we're actually making it 4 times bigger. If we make it 3 times bigger, it's actually going to be 9. If it's 4 times, it's going to be 16, because we're squaring that, because it's growing in 2 directions. That's why we're squaring it. So for example, if the area of one shape is 100 times larger than the area of a similar shape, so we're talking about the area is 100 times bigger. Well, that must mean it's 10 times bigger here and 10 times bigger here, because 10 times 10 is 100. So if the area of one shape is 100 times larger than the area of a similar shape, then what is the ratio of the corresponding sides? Well, I would say that the sides are 10 times bigger in this direction and in this direction. And that's what gives you your area growth of 100. And again, I hope that makes sense. All right, so at this point, I believe I need to close this and reopen it, because it doesn't seem to work well when I add a second one in. So I haven't made a video in a couple days, so I've forgotten some of this already, how this stuff works. All right, so 855. Use your observations and patterns from problem 854. And as always, guys, on these videos, don't forget, you should be pausing these videos and trying these problems. Don't just watch it straight through, watching me do it. So Kelly's shape at right has an area of 17 meters squared. If she enlarges the shape with a linear scale factor of 5, so she's going to make it 5 times bigger in this direction and 5 times bigger in this direction. Well, I hope we all agree that it's going to be 25 times bigger. So I'm going to multiply 17 by 25. I think it ends up being 425, but I have a calculator right here. I'm going to confirm that. And it is 425. So we would get 425 millimeters squared. And again, that's because it's 5 times bigger in this direction and 5 times bigger in this direction, so 25 altogether. And then we'd have to multiply by the original 17. So examine the two similar shapes at right. What is the linear scale factor? Well, this has an area of 656. This has a side length of 40, and this has a side length of 10. So it appears to be growing 4 times in this direction and 4 times in this direction. So going in this direction, it's 16 times bigger. Well, I have the area of the bigger one, and it's asking for what's the area of the smaller one. Well, if I have to multiply by 16 to get bigger, then I guess I have to divide by 16 to get smaller. So again, I'm going to go over here, and I'm going to say that and just to see the ratio, the small one times 16 would equal 656. So I'll divide by 16, and that's why I'm going to divide 656 by 16 again. I have a calculator handy. It appears to be 41. So the area of the small one is 41 units squared. And again, it gets 16 times bigger for the big one. We just work backward on that one. So rectangle ABCD right is divided into 9 small congruent triangles. So you can see we start with the bigger triangle. Is the shaded rectangle similar to ABCD? Yeah, it is. It's got the same shape. It's a different size, right? The scale factor here, it's going from big to small. So don't forget. I've got a phone call. I apologize. I know my phone's loud. Waiting for someone else to answer it. All right, that was pretty quick, actually. All right, so if so, what is the linear scale factor? Well, I'm going from big to small, so I would say the linear scale factor is 3 to 2. And what's the ratio of the areas? Well, it looks like it's 9 for the big one and 4 for the small one, right? Now, while ordering carpet for his rectangular office, Trinh was told by a salesperson that a 16 by 24 costs $800. So 16 by 24 costs $800. Trinh then realizes he read the measurements wrong, and it's actually 8 by 12. So that's no problem. That's half the size, so it'll be $400 instead. Well, hopefully we know that's not true, right? If he cuts it in half this way and he cuts it in half this way, he should be dividing it by 4, not by 2. So this actually should cost $200, and I hope that makes sense why. And finally, if the side lengths of a hexagon triples, how does the area increase? And again, I hope we're all good with the idea by now that it's growing 3 times in each direction for a grand total of 9. So it will be 9 times bigger. First, make a prediction. Confirm a prediction by calculating and comparing the areas. Well, here on this one, and this goes back to the last lesson, but we need to get the areas of these hexagons. So we're going to break these up, and we're going to get those areas. It sounds like I actually have a phone call right now that I need to hop off for. So I am going to just jump to the areas of 856. I hope you guys remember from the earlier lessons that we just did a couple days ago. But it looks like one is 260 and the other is 2338. If I divide 2338 by 260, I get 8.992307. You can see there's some rounding going on there, so indeed it was 9 times bigger. I apologize, I had to skip that, but there's 0% chance that I'm going to make this entire video and lose it just for this one problem at the end. So hopefully you guys remember that from the earlier videos. If not, watch, I guess, 821 and 822. Have a great day.